Okay, so here let's take a look at a sample problem. So it says a uniform magnetic field B with magnitude 1.2 millitesla. Okay, so I just forgot to mention the SI unit for the B field is Tesla. Okay, Tesla. Okay, so it is named after the scientist Tesla, not actually the electric car one. Yeah, of course. Yeah, the electric car one is named after that also. Okay, so call it Tesla. Oh, it's directly vertically upward throughout the volume of a laboratory chamber. Okay, so here you can see B field with a green dot. Green dot means pointing out of the page. Pointing out of the page. If it is deducted like this with a cross, okay, this is pointing into the page. Into the page. Okay. So yeah, for the dot, or sometimes it is like a dot in a circle, then it is out of the page. Okay, so a proton with kinetic energy 5.3 mega eV. Okay, hope you still remember this unit. This is not a proper SI unit, but usually used for the particle physics. So if you still remember, to convert the EV to joule, it is like multiplying by 1.6 times 10 to minus 19, which is the elementary charge. Okay, so enter the chamber, moving horizontally from south to north. Okay, so this is south, this is north. Okay, which means that in this figure, the charged particle is moving upward because this is a proton. So it has plus E charges. Okay, so what magnetics deflection force acting on the proton as it enters the chamber? The proton mass is this one. Okay, neglect the Earth's magnetic field. Okay. Okay, so this is easy. So first of all, we need to know what is the velocity, because it is given that the kinetic energy. So at least you know K equals 1/2 mv squared. Okay, this is the kinetic energy. So actually we can use this to calculate the velocity or the speed of the particle by moving this thing to the left side and then take the square root. So we have a 2k over L and then take the square root of the whole term. So we have a 2 times k is 5.3 times 10 to the 6th power, and then times 1.6 times 10 to minus 19, and then over the mass of the proton, 1.67 times 10 to the negative 27th, and then take the square root of the whole term. So the velocity is nothing but 3.2 times 10 to the 7th power meter per second, which is quite fast. More than 1/10 to the speed of light. Yeah, which is really fast. Yeah, so in that case, we will be able to find the Lorentz force FB to be Q, absolute value of Q times V times B times sine of phi. Okay, so actually V is pointing upward, B is pointing out of the page. They are perpendicular to each other. So this phi is 90 degree. This is 90 degree. So actually this thing is 1. It's a 1. So it shrink down to be Q times V times B. So we just need to plug in the values. Q is positive E, which is 1.6 times 10 to minus 19. And then times V is the 3.2 times 10 to the 7th power. And then times B is this one, 1.2 times 10 to the minus 3rd power Tesla. Okay, so this is nothing but 6.1 times 10 to minus 15. 10 to minus 15 Newton. Okay, so this is the force. It looks quite small, but actually this force is acting on a proton. Okay, so you can imagine if we try to calculate the acceleration, of course it is not asked by the question, but at least you can simply calculate it like FB over M, FB over M, which is actually this 6.1 times 10 to minus 15 over 1.67 times 10 to minus 27. Okay, so this number is really large, 3.7 times 10 to the 12th power meter per second square. Okay, so this is really large. Compared with the G is 9.8 times 9.8 meter per second square. Okay, so I think you can remember this number. So this is much larger than that one. So that's why I said the electromagnetic force generally is much larger than the gravitational force. The gravitational force is weak. Of course, we can feel the gravitational force of the Earth, but of course the Earth is much heavier than us to make the gravitational large enough for us to be feel. Okay, so yeah, so this is this. Okay, oh, actually we need to calculate it. So yeah, so just okay, I do not repeat. It is just like a to b 3.7 times 10 to 12 meter per second square. Okay, so this one is much larger than G. Okay, yeah. Okay, so actually here we cannot I cannot demonstrate it again because it used the JavaScript. So here now the JavaScript is fading, has already faded out for several years, so I cannot demonstrate it to you. But yeah, actually there are some simulator there. So yeah, but anyway, just skip it. So here we talk about the cross field. Just as what I mentioned, the cross field is the perpendicular B field and E field. So here in this figure, we can see the E field is generated by the parallel plate. You can call it a capacitor. So this is a positive plate, this is a negative plate. So it will generate the E field pointing downward. Of course, the magnitude is also uniform. And then here we also assume that B field and uniform E field, a uniform E field is generated also between this plate, but is pointing into the page. So the B field and E field are perpendicular to each other. So we call it the cross field in this region. Okay, so yeah, so it sets a modern version of J.J. Thomson apparatus for measuring the ratio of mass to charge of the electron. Okay, mass of, yeah. Yeah, so it tried to create this apparatus or the measurement setting. Okay, so it is like this is a battery. And then this is a filament. So there will be some electron shooting out in arbitrary direction. But here we have a slit. We have a very narrow slit here, so that if the electron is going horizontally, then it can go through the slit. Otherwise, it may shoot to here and then just absorbed by the boundary. Okay, so if the electron is going horizontally, it can go through the slit and then entering the region of the cross field. Okay, so if we adjust the value between B field and E field to a suitable value, then the electron will go straight. Why we should choose a suitable value? Because if first of all we consider the E field. If this is an electron going through only with the E field, then there will be Fe will be pointing upward. Just say here, Fe will pointing upward, which is opposite to the direction of the E field. And then for the B field, B field is pointing into the page, And then V is pointing to the right side. So V cross B is also pointing upward, but E is a negative charge. So FB will be pointing downward. FB will be pointing downward. If the magnitude of FE and FB are not the same, if FE is larger, then it will go like this. It will go like this. If FB is stronger, then it will go like this. So if FE and FB is equal to each other, then there will be no net force acting on the electron, and then the electron will go straight to the right side and hit the middle point. So based on this, we try to adjust the ratio between the E field and B field, and then make it shooting the middle point. And then we'll be able to know the ratio between the E field and B field. And then this ratio will be related to the mass and also the charge amount, of the electron, which is like if we have a Fe to be the same as Fb, okay, so then we will have Fe will be E times E, and then equals QVB. Of course it is negative E, but yeah, here we only consider the magnitude. Yeah, so this is E, V, and then B, like this. Okay, so E and E will be cancelled to each other. So in that case, we will have E equals VB, E equals VB, or E over B to be V, something like that. Okay, so yeah, in that case, we will get this value. We're able to get this value. Okay, so next, we also talk about very important, I would say important experiment called the Hall effect or Hall effect experiment. Okay, so it says that if we just discuss a beam of electron in a vacuum can be deflected by magnetic field, can the drifting conduction electron in a copper wire also deflected by the magnetic field? Okay, so why this experiment is very important is that it tells you that the moving charge in the wire should be negative charge rather than positive charge. So below we will try to assume the charge to be negative charge first, and then the things will be okay. And then later on, if I remember, I will tell you, if we assume that the moving charge is a positive charge, then there will be contradiction, and that's why the moving charge in the wire should be purely negative charge. Okay, so it says this Hall effect allow us to find out whether the charge carrier in the conductor are positively or negatively charged. Beyond that, we can measure the number of such carrier per unit volume of the conductor. Okay, so it also said that in 1897, this Edwin Hall, then 24-year-old graduate student. Okay, I am master of, yeah, I'm not very this PhD student, 24-year-old graduate student at Johns Hopkins University showed that this one. Okay, so here, so it said that a copper strip with width D. Okay, so this is the width. This is the width. Okay, so here width is the width carrying a current I, whose conventional direction is from top to is from the top, which means that the current is from top to bottom, Okay, we know if it is positive charge, which means that the positive charge should be going like this. The positive charge should be going like that, or if it is a negative charge, it should be going in the opposite direction. Before that, we don't know which one is correct yet. But of course, here we try to make the assumption, okay, for if it is a negative charge, and then everything will be okay. And then if it is positive, then there will be a contradiction. And then I'll show these cases later after we finish all this part. Okay, so let's keep this as the first assumption. Okay, we have a negative charge moving upward. Okay, so this is a negative charge moving upward. Okay, so you can see if the negative charge is moving upward, which means that we have a VD. VD is pointing upward. Okay, and then here we try to apply a B field is pointing into the page. So we show by this green cross here. Okay, so the B field is pointing into the page. So in that case, we try to see what is the direction of V cross B. V cross B. V is pointing upward. B is pointing into the page. So if we just use the right hand rule, so V cross B will be pointing to the left side. Sorry. This is V cross B, pointing to the left side. And as much as this one is a negative charge, so FB point to the opposite side, which means that FB point to the right side. Okay, so here we have a FB point to the right side. Okay, so interesting things start to happen. So if we have a force pointing to the right side acting on the negative charge, okay, which means that there will be negative charge accumulating on the right surface, so that there will be like a negative charge on the right surface, and the positive charge will accumulate on the left surface, because there shouldn't be any excess charge on the wire. The total charge should still be zero. Of course, the charge will keep moving, but yeah, as much as there are force acting on the negative charge to the right side, so there will be negative charge on the right side, accumulate on the right surface, and in that case, the left side will be lack of electron, so that positive charges accumulate, induced positive charges accumulate on the left side. In that case, it is somehow like a capacitor. So there is some positive charge on the left side and then negative charge on the right side. So these charges will generate the E field pointing to the right side. Of course, this is a conductor, and inside a conductor, there are E field. But in that case, since there is external B field, so this makes things more complicated than before. Before I told you inside the conductor there shouldn't be any E field. In that case, we we have not assumed there are some B field there. So in that case, in here we have some external B field, so that there will be E field inside the conductor. Okay, so yeah, so there is E field pointing to the right side. So and then more complicated things start to happen, and more interesting things also start to happen, which means that due to this charge, generate the E field point to the right side, and then this is a negative charge. So this E field will have electric force, electrostatic force acting on this negative charge, point to the left side. Okay, so just now the FB point to the right side, still point to the right side, and then as much as the charge start to accumulate on both surface, positive charge on the left surface, negative charge on the right surface, then it generates the E field. This E field will make there is electrostatic force acting on the negative charge point to the left side. Okay, so there is two force, Fe point to the left side, Fe point to the right side. And then at the beginning, Fe is small because there is less electron accumulating on the right side. But as much as so at the beginning, Fb is larger. Fb is larger, and then the negative charge start to accumulate on the right surface, and then it will make Fe to be stronger and stronger. So until Fe and Fb are equally large, and then there will be no net force acting on the charge anymore, and then it will become an equilibrium state. 它就会平衡了。Okay, so finally, it will stable. The final state is like Fe and Fb have the same magnitude but points to the opposite direction. So no net force acting on the charge. But in that case, we can really measure there is some potential difference. There is some potential difference on the left and right surface. This is so-called the Hall this is actually the Hall effect. This is actually the Hall effect. We can actually measure the potential difference between the left surface and the right surface. Okay, so here it says when a uniform B field is applied to the conducting strip carrying current I, the field perpendicular to the direction of the current, a Hall effect potential difference, which is actually this one and this one, the left surface and the right surface, we have a potential difference called the Hall effect potential difference. V is set up across the strip. Okay, based on this, we can do some calculation. Okay, so first of all, at the equilibrium state, Fe and Fb should be the same. So we will have QE equals QVdB. Okay, QE equal QEdB. So this is for the equilibrium state. And also, we know that the E field is uniform. It is like a parallel capacitor. So E field is uniform inside this region. So we will have V equals E times D. Okay, and also in the pure physics chapter, we have another formula like J equals NE times VD. So we move over the NE, so it makes it like VD equals J over NE. Okay, so in this case, we try to eliminate E and VD. Okay, which means that we try to plug this one into here, or we try to multiply these two equations together and then cancel E first. So first of all, let's say we can have E equals V over D and then plug this one into here. So we will have Q times V over D equals Q times VD times B. So we can do some cancellation. We can cancel Q and then we can cancel no more. So first of all, we can get V equals VD times B times D. Okay, this is a useful formula also. So we just highlight it here. Of course, this VD and this V are the same thing. Okay, so this V just stand for the speed of the charge particle. Okay, so V, this is the Hall effect potential difference. V equals V, small v is the velocity, and then times B is the external B field, and then the D is the width of the strip. Okay, so we have this one, and then we can also try to move VD to be V over B times D, and then plug this one into here. Okay, so we will have V over BD equals this one, J is the current density. It will be I over A. So we have I over NEA. So we have here I over NEA. Okay. So in this case, we can just move. Let me see. We can just keep N to the left side and then move this thing to the right side. So it will become N to be. We go to the bottom. So VEA, and then we have BDI like this. Okay, of course, this is a little bit different from the highlight equation. Here, the point is that we also have this L. We have this L is the thickness of the strip. thickness is in this direction, so I cannot show it here. So this is the thickness, which is like if we have a strip like this. Okay, this is L, this is L, and then A is the cross section area. A is the cross section area. A is the cross section area. A is the cross section area, and then D is the width. So we have L times D to be A. So here we have D over A to be 1 over L. So we will have BI here, and then VE, and then D over A is 1 over L. So we have L here. So finally we get this one. Okay. So here we have a we have a DL to be A, DL to be A. Okay, so we can really derive this one. So for this one, based on this Hall effect experiment, we will be able to find the carrier density because B field is what we provide, so we know this value. I, the current, can also be measured, so we also know this value. V is the Hall effect potential difference between the left side and the right side, so we also can measure this value. L is only the thickness, of course we know that, and then E is the electron, the elementary charge. We also know this value, so we can, based on this experiment, we can measure all this value so that we will be able to use this equation to calculate the carrier density N. Okay, so for the Hall effect, we have this one and then this one, these two equations to be important. Okay, so just now I mentioned that this Hall effect also tells you that the moving charge particle must be negative. Okay, why? If we really assume this is a positive charge, what will it be? Okay, so here, if we assume this is a positive charge and then follow this current direction, which means that VD is pointing downward. Okay, still we have the B field pointing into the page. We have B field into the page. So V cross B. V cross B. V is pointing downward, B is pointing into the page. So in that case, this is V cross B pointing to the right side. V cross B pointing to the right side. And this is a positive charge. So FB also point to the right side. In that case, the positive charge will start to accumulate on the right side rather than the left side. So in that case, it turns out to be positive charge accumulate on the right side and negative charge accumulate on the left side, which is the other way around from the measurement result. In the measurement, we can really measure that the left side should have a higher potential rather than the right side. So this is a contradict with the measurement result. So this tells you that it is impossible that the moving charge particle in the wire to be positive charge. Okay. Okay, so here we have a sample problem, number 2. Okay, so it says a solid metal cube. Okay, this is a metal cube of edge length d, moving in the positive y direction at a constant velocity of magnitude 4 meters per second. So the cube moves through a uniform magnetic field of magnitude 0.05 Tesla in the positive z direction, which cube phase is at low electric potential and which is at a higher electric potential because of the motion through the field. Okay, so just now the Hall effect is like if we have a wire and then we provide some current, and then there is a external B field perpendicular to it, that will be Hall effect. This case is a little bit different, but it turns out to be it turns out that the Hall effect still occur. This case is like we have a metal cube. So in this metal cube, there will be some free electrons. If we try to move this whole cube in the magnetic field, and the velocity and the magnetic field does not point to the same direction. Of course, in this case, the velocity and the B field are perpendicular to each other. There will also be Hall effect. Okay, so the first question asks you what is the direction, or what is the or at least it asks you which phase will has the higher electric potential because of the Hall effect or because of the motion through the field. Okay, so here, if we try to move this cube, there will be some electron, okay, moving upward. Okay, this is a negative charge. Okay, so here V cross B, V points to the y axis, and then B points to the z axis. Y cross Z will be x axis, positive x axis. Okay, so this is V cross B. This is V cross B, and in that case, FB points to the opposite direction because this is a negative charge, which means that the answer will be like this side will have a lower electric potential, and the right side will have a higher electric potential because the E field, the electron, there will be FB acting on it pointing to the left side. So the electron will accumulate on the left side, and then okay, there will be positive charge on the right side. And of course, if more and more electrons accumulate on the left side, it will generate the E field pointing to the left side, and then start to so the FE will become larger and larger, so that as FE and FB really cancel each other, and then the electron will not accumulate anymore, and then it becomes the equilibrium state as this experiment. So actually what we provide is different, but it turns out to be the same phenomenon, to be the Hall effect. Okay, so next it asks you what is the potential difference between the phase of higher and lower electric potential. Okay, so here we just need to use V equals VBD. Okay, then this is pretty much it. V is 4 meters per second, and then B is where? This one, 0.05 Tesla, and then times D is 1.5 centimeters, 0.015. So this is nothing but 3 millivolt. Okay, so this value is quite small, 3 millivolt. Okay, so next here we talk about the circulating charge particle. So it says that if an electron or charge particle, so of course in this case it shows an electron entering the B field, and if the V and B E and B are perpendicular to each other, then the electron will be in the circular motion. Okay, so here in the figure you can see a beam of electron is projected into a chamber by an electron gun G. So this is the electron gun G. Okay, so in that case, there are some, let me choose a light color, so that, okay, so this is the initial velocity, and then it says that the electrons enter the place, enter in the plane of the page with speed v, and then move in a region of a uniform magnetic field directly out of the plane. Okay, so in that case, throughout this region, there is a B field pointing out of the page. Okay, so of course here, B and V are perpendicular to each other. So we can see that V cross B. V cross B is pointing upward. Yes, here pointing upward. Okay, so there is yeah. Cross B. Oh, sorry. V cross B. Yeah, V cross B. Let me see. The electron pointing in the page. Okay, V cross. Sorry, it's pointing out of the page, right? Is it entering? Directly out of the page, not into the page. Okay, it should be like out of the page. It should be out of the page. Okay, it should be like this. Okay, so V cross B. V is pointing to the right side, B is pointing out of the page. So V cross B pointing downward, and then it is an electron. So FB pointing upward. Okay, FB pointing this side. Okay, so it will try to turn left. Okay, turn left. Okay, so if it goes to here, okay, the B field also pointing out of the page. So V cross B B point to the right side, and then FP will point to the left side. So it turns out to be a circular motion like this. It turns out to be a circular motion like this. Keep rotating. And then, of course, FB should have a magnitude, Q times V times B. Okay, here we already know that V and B are perpendicular to each other. So we don't have the sine of phi or sine of phi to be 1. So on the left side, we only have Q times V times B. Okay, of course, Q is E because it is an electron. Okay, and then also in physics 1, you should know that this is the, yeah, I think this is the force for the yeah, this is the force for the circular motion, mv squared over r, which is like a equals v squared over r. In high school physics, I think you all also have learned that before. Okay, so this is the force. So this force will be the same, will have the same magnitude as this one. So we equalize them so that we can actually do some simplification. Like we can cancel this v and this v squared partially, so that we can move r to the left side with move qb to the right side. So it turns out that we move this one to the left side, we move qb to the right side, so we have r to be mv over qb, okay, which is actually this one. Okay, so in this case, we know that m is a constant, v is also a constant, although the direction is changing, but throughout this circular motion, v will be a constant, and then q is of course a constant, b is a constant. Okay, so this is a radius. If we would like to make a larger radius, then the v will be larger, because based on so for different circular motion, m doesn't change, b doesn't change, and q doesn't change. If we have a larger v, then there will be a larger r. Okay, so which means that r and v will be perpendicular to each other. Okay, so something like that. Okay, so here we have another sample problem. So it says an electron with a kinetic energy of 22.5 eV move into a region of a uniform magnetic field of magnitude 4.55 times 10 to negative 4 Tesla. The angle between the directions of B and the electron velocity is 65.5 degrees. So this V and B are not perpendicular to each other. So in that case, we need to decompose this V into two directions. This V parallel is parallel to the B vector, and then this one V perpendicular is perpendicular to B vector. Okay, so we decompose it into two directions. So what is the pitch of the helical path? take by the electron. Okay, so what is helical? Helical is 螺旋的路径螺旋形的。So this is like a 螺旋形, okay, helical path. And then the pitch means that actually if you would like to actually you can find an axis for this helical. And then if you just project this helix line onto a plane perpendicular to this line, then they will be the same circle. So in that case, if we try to find for the two adjacent circle, for this point and this point, we measure this distance. This is actually the pitch. This is actually the pitch. Why it will like that? Why it will like that? So just now I mentioned that we can decompose this V in two directions. One is V perpendicular, another one is V parallel. So for this V parallel interacting with this B, as much as these two vectors are perpendicular to each other, so V parallel cross B will be zero vector. Okay, so there won't be any force on this direction, which means that in this direction, it will be a uniform speed movement. Okay, so it's just moving in a uniform speed along this axis. But in the plane I mentioned, for example, if this is a C axis, and then the plane is the XY plane. So in the XY plane, it will be circular motion because this V perpendicular and B are perpendicular to each other. So on the XY plane, it will act like a circular motion. And then XY plane is a circular motion. And then C plane is a uniform speed movement. So it will be like moving up like this. So hard to yeah, let me kill more. At least if you see this one, you can imagine it is like a helix line or moving up like this. Okay, so let's start how to calculate it. So similarly, we get the this is the B field, and then this is the kinetic energy. So based on the kinetic energy, we can calculate the V first. Okay, so first V should be 2K over M, and then take the square root of the whole term. So this is 2 times 22.5 EV, 22.5 times 10 to 1.6 times 1.6 times 10 to minus 19 all over electron. Electron has the mass 9.11 times 10 to minus 31, and then take the square root for the whole term. Okay, so this value will be 2.81 times 10 to the 6th power meter per second. Okay, so this is the velocity. And then it tells you that B and V has an angle of 65.5 degree. Okay, which means that this angle is 66.5 degree. Okay, so actually we can really calculate the pitch as V parallel times T, because in the Z-axis, it is like it moves in this velocity all the way, V parallel. And then T, what is T? T is the pure rate of the circular motion. Okay, in the previous page we have not mentioned, but of course in physics 1 maybe you should have know what is the period of a circular motion, which means that how long does it take to take the particle to go for a single loop. It is easy. It will be like T to be 2 pi r. 2 pi r is the circumference of a circle, and then divided by the V. Okay, so this is the period. This is the period of the period of the circular motion. Okay, so if we just, this is R, and then we plug in this one into there, then we can get the expression in terms of mvqb. Okay, so here it is like, this is v parallel, so this is v cosine of phi, so this is phi, and then we will have 2 pi r. 2 pi r is this one, mv over qb. So we have mv over qb, and then over v. Okay, so here we can actually cancel this v and this v. So it makes it like 2 pi m over qb. 2 pi m over qb. Okay, so in here we can have v to be 2.81 times 10 to the 6th power, and then cosine of 65.5 degree. And then we also have 2 pi m, 2 pi times m. Electron is 9.11 times 10 to minus 31. And then over q, q is actually e, 1.6 times 10 to minus 19. And then times b, b is this value, 4.55 times 10 to the negative 4th power. Okay, so we can just press the calculator. This is 9.16 centimeter. 9.16 centimeter, or you can write it as a 0.0916 meter. Okay, so this is the pitch. This is the pitch. This is the pitch. Okay. Yeah, so here we have another sample problem. Let me finish this one, and then we can have the end. Okay, so so it says the essential of a mass spectrometer, which can be used to measure the mass of the ion. The ion of mass and charge Q is produced in source S. Okay, so this is the source. Okay, so this is the ground. This is the ground. And then with the electric potential V, so there will be some positive charge shooting out, and if it is moving upward, then it can go through the slit. And of course, after shooting out, there will be no force acting on the charged particle. Then it will go in a uniform speed until it enters this region. In this region, we have some B field pointing out of the page. Okay, so there will be Lorentz force acting on the charged particle entering this region. Okay, so it says that the initial stationary ion is accelerated by the E field due to the potential difference V. Okay, the ion leaves S and then enter a separate chamber in which a uniform magnetic field is perpendicular to the path of the ion. Okay, just as what I mentioned. Okay, so a Y detector lines of bottom wall of the chamber, and then cause the ion to move in a circular, in a semicircle. Okay, of course it should be a circular motion, but here, as it enter here, so it will just move in a semicircle, and then there is just like a wall, and then the charged particle will hit on this detector. This is so-called the detector, 就是侦测器. Okay, and then it will know that what is the position this charged particle hit on this wall. Okay, and then based on measuring this distance, and then you will be able to find something interesting. Okay, oh yeah. So a Y detector line at the bottom wall of the chamber, and then cause the ion to move in semicircle and thus strike the detector. And then suppose that B is this value, and then V is this value, and then the ion charge Q strike the detector at a point at X. So we will be able to measure this X. And then it asks you what is the mass of the individual ions in atomic mass unit. Atomic mass unit, 1U is 1.66 times 10 to minus 27 kg, which is actually the mass of a proton. Okay, so here we would like to find what we would like to find. Let me see. We would like to find what is x. We would like to find what is this value. What is this value? Okay. Okay. So first of all, there are some electric energy to accelerate this charged particle from no potential energy. So there will be something like the conservation of mechanical energy, which means that delta K plus delta U to be 0. So this is the conservation of mechanical energy. Okay, so the delta K, at first, the charged particle is stationary, which means that V is 0. So finally, we will have half of mv squared. So minus 0 to be the delta K. And then for delta U, it will be 0 minus QV. 0 minus QV, because for this one, this is ground. So we won't have any potential energy. And then here, we will have Q times V. So we have 0 minus QV to be like this. So in this case, we will be able to find V to be QV, 2QV over M, and then take the square root, something like this. And then this is a circular motion. Of course, this is only a semicircle, but at least this equation still correct R to be mv over qb, which is the radius of the circular motion. And then we can plug in this v here. So we have m over qb and then times square root of 2qv over m. Okay, we just plug in this one in the radius formula. Okay, so here we can actually cancel something. Okay, here we have square root of q, we have q, and then we have m, we have square root of m. So we can just do something like b, 1 over b, and then square root of 2 mv over q, which means that we try to put this one inside, put this one inside. So after putting this m inside, it becomes m squared, so that it cancels with this m. Okay, so we have 1m on the top, and then this q inside will become q squared, and then cancel with this q, so we have q at the bottom, so it will be like this. And then we also have r is the radius, but here this x is like the diameter, which means that r equals x over 2. R equals x over 2. So this is the diameter, this is the radius. Okay, so in that case, x will be 2r, which means that it should be 2 over b and then times square root of 2 mv over q. And then finally, we would like to find, not x. We are not going to find x because here we already provide x is this value. Finally, we would like to find what is the mass of the particle. So finally, we should have m to be b squared x squared q over 8 v. Yeah, like this. Yeah, we move all the things except m to the left side and then take the square on both sides. Then we will have this one. Okay, so we can just plug in all the values. Okay, it will be like b is 80 millitesla, 80 times 10 to the negative third power, and then quantity square, and then times x is this one, 1.6254 square, and then times q is this value, 1.6022 times 10 to negative 9. Okay, no need to square, and then over 8 V is 1000 volt, 1000. Okay, so finally M will be 200, sorry, it should be 3.3863 times 10 to negative 25 kilogram. Okay, this is in SI unit, but it asks us to represent this mass in the atom mass unit, which means that we would like to divide the value by this 1.6605 times 10 to minus 27. So by dividing it by 1.6605 times 10 to negative 27, it becomes 203.93 U. Okay, so this is the final answer. This is the final answer. Okay, and based on this, we will be able to know how much like a proton plus neutron are in this particle. Yeah, because a proton and a neutron should have almost the same mass, not exactly the same, but almost the same mass. So it is like almost 204 U. So P plus N, the number should be like 204 based on this experiment. Okay, so let us start.